Up our lecture on statistics, and then we're going to talk about ethics in research, ethical considerations, and then we're going to look at a couple of famous experiments that have been done in the past, which are really, really interesting and just profoundly unethical, as are examples of what not to do today. So, to finish up our talk on statistics, we're going to look at standard deviation. Standard deviation is the measure of data points that are gathered during an experiment. So if you're measuring, um, to go back to, how many hours a night high schoolers sleep, uh, you're going to send out your surveys and then you're going to get them all back and then you're going to start plotting out your results. And what you're going to find is that uh, lots of people have lots of different answers. And the standard deviation is going to let you know, do you have scores all over the board or are most of your scores kind of lumped together? And so if you have a low standard deviation, that means almost all of your scores were pretty close to each other. If you have a really high standard deviation, that means people were sending in results all over the place. So some people were saying that they're sleeping 2 hours a night. Some people are saying that they're sleeping 15 hours a night, and you've got scores all over the scatter plot. So let's look, oh, sorry, went the wrong way. Let's look at an example here. So a normal distribution is when our scores sort of end up looking like a bell curve. And we'll take a look at that in just a second. But if you're plotting out your scores, and you can see them here, most of the scores fall around our median. In this case, scores between 0 and 100. 50 is our mean, and most of those scores are falling a little bit above or a little bit below our mean. In this case, our standard deviation is 20 because the average distance between all of the scores and the mean is 20. And so if we put those scores onto a bell curve, it looks just like this. And this lets us know we have a normal distribution. We have half of our scores above the mean, and we have half of our scores below the mean. And that's what makes it a normal distribution. 50% of your data points are going to be left of the mean, and 50% are going to be right of the mean. Now, the vast majority of your scores are going to fall within let me say that differently. Most of our scores are going to be sitting right around the mean. And so when you look at this bell curve, you can see this is looking at IQ scores, and the average IQ score is 100. And so 68% of our scores fall in between 15 points of that mean. So in between 85 and 115, we have 68% of our scores. That means 34% are within 15 points below the average, and 34% are within 15 points of above the average. Now, this is important because when you look at these white lines that are dividing out the bell curve, we've got lines at 85, 70, 55, 115, 130, and 145. In between 100 and each of those lines is 1 unit of standard deviation. Okay, so if I tell you that, if I get all your tests back next week, and then I tell you you're within one standard deviation above the mean, that lets you know you scored better than half the class.
Tell me what?
But you were within that first standard deviation step. Now, if I told you that you were 2 standard deviations above the mean, that means you scored really well, okay? That means you scored better than 84% of your classmates, because 50% of your class scored below the mean, 34% of your class scored within 1 standard deviation unit, and you scored above that. You were in that orange section there. If I said you scored 3 standard deviations better than the mean, that means you were in the top 2% of the class. You were in that light blue area. Now, these numbers, right? +2 standard deviation, -1 standard deviation. These are known as the z-score. And this is an important term. It's not on here, but you need to write it down. The z-score will be in between -3 and +3. -3 means you are in the bottom 2% of the class. You don't want a z-score of -3 when we're talking about your test score. If you got a z-score of +3, you would be very, very excited because you were be in the top 2%. Okay. If you scored a z-score of +2, you're in that orange area, and that means you're in the top 16% of the class and you scored really, really well. Okay. Does that make sense? We'll talk about it on Monday a little bit more if you still have questions. Now, sometimes when you're recording your data, you end up getting these scores that are way out of whack with everybody else. Maybe on next week's test, everybody scores about a 80%, and then one person scores 100%. And so it moves the mean away from everybody else's scores and towards that high score because one person scored so high. Or maybe everybody scores about an 80% and then one person scores a 2%. That's really going to pull the mean down towards that 2%. Even though most people scored around 80, the mean is going to be less than that because that really low score pulls the mean down. This is known as a skewed distribution. Okay. If someone scores a crazy high score and it pulls the mean up, that's a positive skew. That's the picture on the top picture on the right. Okay. And it's a positive skew because most people scored in that giant bulk of scores, but a couple of people scored really, really high, and that pulls that tail to the right. So if you think of this as an animal, the direction of the tail tells you which way the graph is skewed. In this case, the graph is skewed positive because the tail points to the right. If someone scores that 2% and they pull the mean negative, they pull the mean to the left, you end up with a negative skew, which is the second graph. If everybody scores about the same and then you plot out your scores and you have that nice bell curve, then you have a normal distribution. Good. So when we look at the income per family, let's say of a group of students, and most families make about the same amount, but then you have a couple of families that make a lot of money, you end up with a graph that kind of looks like this. So most of the people fall within that 15 to 45 range. But then there's a couple of people who are making a ton of money, right? So most people are falling in that $15,000 to $45,000 per year. But you got these two families way out on the right making $475,000 or $710,000. That's really going to skew our results. And so what happens is the mean gets pulled away from the mode and the median, and it gets pulled to the right, and that's a positively skewed distribution. All right. So we've already talked about correlation. It's the relationship between variables where if one variable changes, the other variable reflects that change as well. Now, we try to measure the strength of that correlation. And you're not going to have to worry about the math here at all. All you need to be able to do is read the results. And the results always come in the form of a number between -1 and +1. So it's going to be 0.8 or it's going to be -2, but it's always going to be between -1 and 1. If it's higher or lower than that, then you've really screwed up your math. So if someone says, yeah, my correlation coefficient of my experiment is amazing, it's 2.4, then you can tell them, well, then you've really done something wrong because it can't be. It has to be between -1 and 1. And the closer it is to 0, the weaker the correlation. So if you're at -0.99, that means you have an almost perfect negative correlation. Or if you're at positive 0.92, you have an amazingly high positive correlation. You're never going to see a perfect correlation. You're never going to see a -1 or a 1. If you get anything above like a negative, if anything above a 0.8 or below a -0.8, you have a really, really strong coefficient or a correlation. Anything close to 0, and you have a very, very weak correlation. So if someone says, my correlation for my study was 0.03, you can tell them, well, that's a really, really weak correlation. So we've already talked about this. The coefficient is the statistical measure of the extent to which two factors relate to each other. Okay. The positive or negative tells you whether the correlation was positively correlated or the correlation was negatively correlated. A negative correlation doesn't mean like it's low. It just means it's negatively correlated, right? So as drug use goes up, GPA goes down. That's a negative correlation. And it's probably going to be a high negative correlation. It's probably going to be negative 0.7 or 0.8, right? If it was negative 0.1, then it's a weak correlation. Now, if we plot out our data results, we can see that correlation, right? So this the scatter plot on the bottom left, okay? The line is going up and to the right. That means it's a positive correlation. If the line, like in the middle scatter plot is going down as it goes to the right, that's a negative correlation. And then sometimes we don't see any organized correlation at all. Like in the case of the scatter plot to the right, you just got data points all over the place. There's not an obvious movement. That's when there's no correlation at all. So, which is stronger? Which is a stronger correlation? Negative 0.13 or positive 0.38? Oh, whoops. Okay, you should have guessed 0.38 because it's farther from 0. Negative 0.72 or 0.59. You should have guessed negative 0.72 because that's farther away from 0. Or negative 0.91 or 0.04. You should have said negative 0.91 because that's really far from 0. Remember, if you get outside of -1 or 1, then you just made some sort of computational error. You're never going to have numbers outside of -1 and 1. All right. Sometimes we already talked about this, illusory correlations, or when we see correlations where there simply is no correlation. Famously, people say that if you go outside and play in the cold with no hat on, you're going to get sick. That's not true at all. There's no actual correlation there. Now, maybe you go play out in the snow and the next day you're sick, but that's just bad luck. All right. So a lot of times we use scatter plots to record our data. We just looked at a couple seconds ago. I'm sure you've seen this before. When you plot out your data, it's going to be, well, in some cases, it's going to be all over the map. If you've got points everywhere, then you've got really low correlation. If all of your points are centralized or close to together, they're really clumped together nicely, that means you have high correlation. Okay, so we talked about z-scores when we looked at that bell curve. A positive z-score means that you're above the mean. A negative z-score means that you're below the mean. A z-score of 0 means that you scored the same as the mean. And so when we look at our bell curve here, you can see we've got 3 units of standard deviation to the right and 3 units of standard deviation to the left. And remember, 68% of scores in a normal distribution are going to fall within one z-score of the mean, either a -1 or a 1, right? And 90, what do we see here? 94% are going to fall within 2 standard deviations of the mean. So if you scored a +3 for your z-score on next week's test, that means you scored really, really well. You scored in the top 3% of classmates. Right. Inferential statistics lets us know. So inferential statistics tell us how strongly we can predict future outcomes based on our data. So if we just do a descriptive analysis, like we do a case study, we said this before last week, case studies don't tell us excuse me, anything about what might happen in any other situation. The case study tells us what happened to this specific subject in this specific environment. But if we do a laboratory experiment, the whole point of a laboratory experiment is that we actually can create causal relationships between variables. We can explain this happened because of that, and then we can predict in the future what the likelihood might be of a similar outcome. Inferential statistics tell us the reliability of those predictions, okay? And again, you're not going to be expected to know how to do any of this math. You just need to know how to read the results. And the results are going to come in the form of a p-value. The p-value tells you the likelihood that those results were the result of chance. And you want your p-value to be as low as possible. So if you do a giant research project and at the end of the day, you measure your p-value and it's a 0.3, that means there's a 30% chance that all of your results were the result of chance. And that's bad. You don't want that. You want your p-value to be low. You want it to be as low as possible. It's never going to be 0, but you want it to be below 5%. That means if your p-value is 0.05 or less, there's less than a 5% chance that your results are due to just chance, and probably your results are reliable. So that 0.05 number is really important. If your p-value is above 0.05, your research probably isn't reliable. If it's 0.05 or below, it's considered reliable. And that's what you really have to remember about p-values. You're looking for 0.05 or lower. All right. We've already talked about these types of research: descriptive, correlational, experimental, what their purpose is, how they're conducted, if anything's manipulated, like in the case of an experiment. So you can look over that. All right. So when it comes to psychology, overwhelmingly, our subjects tend to be living creatures, either animals or oftentimes people. As such, there's a lot of rules concerning how you can perform your research. You can't go around blowing people up, feeding them poisonous chemicals, that kind of thing. Nor can you intentionally mess with their heads in such a way as you can actually do real damage. Because historically, and you'll see a couple of examples, experiments have been done on people that have really left long-term negative psychological consequences. And so today, we have to be really careful to avoid undue harm on people physically or psychologically. As such, we now have this organized committee, the IRB, the Internal Review Board, and they review all experiments before they're performed, and they have to give their okay, or the research cannot be conducted. Some of the requirements today in order to do human research include consent must be given. The participants must be informed as to what's going to take place, and then they have to willingly give consent. You can't force people to do anything they don't want to do. Deception in some cases is required. Sometimes the participants can't know what is really going on. You might tell them that you're researching one thing when in reality you're researching something else. Maybe you're studying levels of anxiety, test anxiety. You might tell them that you're giving them a reading test because you want to measure the reading comprehension of high schoolers, but in reality, you're measuring their anxiety. Uh, Sometimes that's necessary. Um, if telling them ahead of time, hey, we're studying your anxiety, that's just going to make your results less reliable if they know that it's coming. So if it's unavoidable, you're allowed to use deception. If you don't need to deceive the participants, then you shouldn't use it at all. If you, in all cases, but especially in the case of deception, as soon as the experiment is over, you need to debrief. You need to explain to them what happened, what was going on, what you did, what you're studying. Um, they need to understand the purpose of the experiment and how the results are going to be used in the future. They, of course, um, always have to have the right to withdrawal at any point that they say, you know what, I don't want to do this anymore. They have the right to quit, and you can't keep them there. We'll take a look at a couple of examples where that was ignored and people were forced to participate in experiments much longer than they wanted to. They have to be protected from harm. You can't allow them to be in any kind of situation where they're going to get hurt, either physically or psychologically. Um, their confidentiality must be ensured. You can't use real names. You can't post their image. You can't use any of those kinds of things. In your results, you should always use pseudonyms, that kind of thing. And then you can never improperly observe people that are unaware of it. Their privacy must be maintained. You can't just go out and draw research from people that have no idea that it's going on. And of course, sometimes we go out into the world and we try and observe people in their natural state, obviously, naturalistic observation, but even that has to be done appropriately. It's one thing to be watching people in the lunchroom. It would be totally inappropriate to watch them, say, in the bathroom. All right. When it comes to animal research falls under the three R's of ethical treatment. Replacement. Animals should be replaced with the lowest level life possible that still creates accurate, useful data. If you don't have to perform an experiment on a horse or a monkey, if you can do that same experiment on a cricket or an ant, then you should use the form of the lowest developed form of life possible. Two, refinement. We need to reduce the amount of harm inflicted on the animal as much as possible in whatever the least invasive form of the experiment that's still productive can be. That's the form we have to use. And then lastly, reduction. Whatever the lowest number of animals necessary for the experiment to get valid conclusions is, that's the number we should use. If we only need 3 animals to draw our conclusions, then we should only use 3. We shouldn't use 30. You can read through this chart on your own. We actually don't talk a lot about the ethical treatment. Like we're more concerned with ethical treatment of humans. Like I said, most of our research, most of this class is spent on human psychology. So of course, the way we treat animals in studies is incredibly important. You're just less likely to be tested on it. So read through this. But as far as what you need to know for our exam, it's going to be the ethical considerations for human research. All right. Um, there are two experiments that you need to be familiar with. There's Milgram's experiment, and then there's the Stanford Prison experiment. You may have heard of either or both of these. Go into the other, just the actual PowerPoint, and click on these links. There's hyperlinks for each of these, and they're short videos. You need to be familiar with what happens in the experiment and the problems with those experiments ethically. We'll talk about that briefly on Monday together. But you need to watch each of these videos and be familiar. There's going to be questions on the test referring to both of these experiments, what the results were, and why they were examples of unethical psychological research. Okay, that is it for today. I'll talk with everyone on Monday. We will be taking our multiple choice next week and our FRQ. So multiple choice will be in class. The FRQ you will be taking at the same time as the other class. So if you're at home, you'll be taking the FRQ while the kids in class are taking their multiple choice. I'll set up a team meeting. You'll need to log on at the time of your class, and I'll give you the question. You'll write it out by hand, and then you'll submit to me as soon as you're done. We'll talk more about that on Monday as well, but expect to be participating at the time of your class remotely and doing the FRQ. All right, we'll talk more on Monday. Let me know if you have any questions. Bye.